Welcome back, good morning. So, yesterday we introduced a Poisson process. We said that if you have a counting process, you can think about the counting process in terms of n of t, which is the number of arrivals up to and including time t, or you can look at it in terms of the arrival epochs s i's or the inter-arrival times x i's. If these inter-arrival times x i's are independent and identically distributed, you say that the process is a renewal process. Okay. The counting process is a renewal process. Now, a Poisson process is a very special renewal process in which these x i's are IID exponentially distributed with some parameter lambda. Okay. And we also introduced this memoryless property of the exponential random variable. So, in some sense this exponential distribution forgets what happened in the past. So, which is why this Poisson process is very special. So, we will formalize this in this lecture by proving in what sense this memoryless property actually holds. Okay. So, this lecture we will prove this memoryless property in a more precise sense. We will also discuss we will also basically prove that the increments in a Poisson process are stationary and independent. At this point these terms may not make sense to you, but we will define what this means. Okay. So, this is where we are heading. So, let me state a theorem. Consider a Poisson process of rate lambda and fix any t bigger than 0. The length of the time interval from t until the first arrival after t is a non-negative random variable z with CDF fz of little z is equal to 1 minus e power minus lambda z for z greater than or equal to 0. Further, z is independent of all arrival epochs before t and independent of the set of random variables n of tau for tau less than or equal to t. Okay, this is a slightly long statement, but it is certainly not difficult to understand. So, what you are doing is you consider a Poisson process of rate lambda and you fix any t, all right. So, you are looking at t as far as you are concerned, your observations start at little t. Okay. So, a Poisson process has been running and you show up at some little t and you are looking at when does the next arrival after t come. Okay. Now, so as far as this t is something fixed, it is not random. Okay. Little t is something fixed and you are looking at the next arrival to come after little t. Okay. And from t until the next arrival, this interval is denoted by z. It is some random variable, right? It is some non-negative random variable, right. What this theorem is saying is that this time to the subsequent arrival after little t is exponentially distributed with parameter lambda. Okay. It is same as an inter-arrival distribution, right, same as the original inter-arrival distribution, and furthermore z is independent of everything that happened in the past. It is independent of how many arrivals came so far, it is independent of when those arrivals came, right, and until at time t some arrivals would have already come, right. and the time to the subsequent arrival after you show up at t is independent of how many arrivals came and when they came, that is what this theorem is saying. Okay. So, it is like buses are going at a bus stop according to some Poisson process, you show up at some particular time. Okay. The time that you wait for the next bus will still be an exponential random variable, okay, and it will be independent of how many buses came in the past and when they came, if the bus arrival process is a Poisson process, which it is usually not, right. Okay. Clear, statement is clear. So, just to show it in pictures, so that is your time axis, so this is 0. So, some arrivals have showed up, right. So, this is, so this guy is x1, this guy is x2 and so on, right, these are inter-arrival times. You are picking some time t, right. The arrival after this comes here, okay, and the z that is of interest is this guy. Okay. So, you are showing up at time t and you are looking at the time to the next arrival. Okay. What this theorem is saying is that z is exponentially distributed with parameter lambda and z is independent of the arrival epochs of all these previous guys and also the number of those arrivals. Okay. So, it is independent of everything that happened in the past, that is what this theorem is saying. Okay. Now, let us prove this. So, we will first start with so let us say let t be such that n of t is 0, okay. This is case 1, this is like case 1, okay. We will consider two different cases, n of t is 0, n of t is strictly bigger than 0, okay. So, we will look at the following. So, you look at, let us just draw a picture to make this clear. This is 0, time t equal to 0, your time t is here, no arrivals have come so far, n of t is 0, the first arrival comes somewhere here, okay. That is the case we are considering and that is your z at this point, right. Now, we are looking at, let us consider probability that z is bigger than little z given n t equal to 0. Okay. Now, you recall the following, we showed yesterday that the event S n less than or equal to t the same as the event correct, this we showed yesterday, yeah, did I write it down correctly, sorry, did I write it down correctly. So, now this is the same as saying that the event S n bigger than t, I am just taking complements, the same as the event n t less than n, just taking complements, correct. If A is equal to B, A complement is equal to B complement, right. So, from here you can see that n t, so in particular you can write that the event n t less than 1, which is just equal to the event that n t equal to 0 is same as the event that S n is S 1 is bigger than t, correct. So, n t less than 1 is same as the event n t equal to 0, because n t takes only non negative integer values and n t less than 1 is same as S 1 bigger than t from here, correct, but S 1 is same as x 1, correct. So, I can just write this guy as probability z bigger than little z given x 1 bigger than t, correct, because the event n t equal to 0 is same as the event x 1 bigger than t. So, it comes from that box, okay, from the recall box. So, this is simply, this is just equal to what, probability that, so z is nothing but x 1 minus t, right. So, this is the same as probability that x 1 bigger than t plus z, given x 1 bigger than t. Okay. From the picture it is clear, right. So, this guy is x 1, correct. So, what is probability that x 1 bigger than t plus z given x 1 bigger than t? So, this x 1 is exponentially distributed and we know that it follows the memoryless property, right. So, this is equal to probability that x 1 bigger than z. This is due to this equality is due to memorylessness, correct, and this is nothing but e power minus lambda z, all right. So, for conditioned on n t equal to 0, z is exponentially distributed with parameter lambda, right. Now, we also have to look at n t bigger than, I mean n t equal to some n bigger than 1. In both these cases, if this holds, then the unconditional distribution of z is exponential, right, that can be that follows. So, let us consider case 2. Let us say n t equal to n, some bigger number bigger than or equal to 1. Okay. So, let us say, so n t there have been some n arrivals, correct, n arrivals have already occurred at time t. Now, let us say that let S n is equal to tau, some less than or equal to t. So, I have said that there are n arrivals. So, that the time at which the nth arrival occurred, I am calling it S n is equal to tau, right, and this has to be before t, right, less than or equal to t, all right. So, here the picture is as follows. So, this is 0. So, some arrival occurred here, some arrival occurred here, some arrival occurred here and so on, all right. So, you are looking at, so this is n t, this is t, sorry, this is the time axis. I am looking at a particular, so this is time, so this is a particular t, okay, all right. In this case, in what I have drawn, n t is equal to 2, right, but it does not have to be 2, this can be anything that is not 0, and of course, your z here is that, right, z is the time to the next arrival, and this is S 2, right, which is this I am calling tau. See, all random variables are big Z. So, I think my big Z's and little z's are looking very similar. Maybe if you can write the a cursive Z, maybe it is better, right. See, always random variables are big. So, what I want to put here is big Z, right. Okay. So, this is big Z. Okay. Now, you consider the following probability that S Z big Z bigger than little z given n t is equal to n comma S n is equal to tau. Okay. Now, we can argue similarly that this is equal to the probability that x n plus 1 greater than z plus t minus tau given n t is equal to n and S n is equal to tau. That is because this, what is this width? This is t minus tau, right. So, this random variable will be bigger than z, some little z, if the n plus 1, this is the nth arrival, right, this is the n plus 1th arrival, right. So, this interarrival time is nothing but x n plus 1, correct. So, x n plus 1 bigger than t minus tau plus little z, correct, comes from the picture directly. So, this guy you want it to be bigger than z. So, x n plus 1 will be bigger than little z plus t minus tau, correct, yeah, obvious from the figure. It is useful to draw these figures just so that you do not make any mistakes. Now, again you can argue this event. So, you are conditioning on S n is equal to tau. and n t equal to n. Okay. So, the nth arrival arrived at some tau and the n of t is still equal to n, which means that there have been no more arrivals, right. You can again argue just like in the previous case, this just boils down to you keep this the same plus t minus tau given x n plus 1 greater than t minus tau, because there have not been any arrivals since, right, and S n is equal to tau. Now is an important step. See, x n plus 1 by the definition of a Poisson process is independent of S n. Why is that? See, actually this is true for any renewal process, right. S n is simply the sum of x 1 through x n, but x 1 through x n will be, they are all IID random variables, right. So, x 1 through x n will be independent of x n plus 1, right. So, x n is independent of S n, right. So, this conditioning can be dropped, right. So, I am going to, so since S n is independent of x n plus 1, I am going to write this as x minus tau given x n plus 1 greater than t minus tau, okay. And this is equal to probability that x n plus 1 is greater than z. This is because of x n's are exponentials, right, x i's are, this is memoryless. Just okay. Actually, if this conditioning, so you see that the conditional distribution of z given S n equal to tau boils down to an unconditional distribution, you can just drop this, right. So, you can see that z is independent of S n. Likewise, if you were to condition on S n is equal to tau, S n minus 1 equal to tau prime, S n minus 2 equal to tau double prime and all that, all those conditionings will drop off, right, because x n plus 1 is after all independent of everything in the past by the definition of a Poisson process. So, this proof itself can be easily reworked to show that this z is independent of S n all the previous arrival epochs, correct. Also n drops off, n t equal to n, you condition on n t equal to n, that also drops off, right. So, nothing would change if you were to condition on n t equal to n and previous n t prime something before t to be n prime and all that, it will still drop off, okay. You can rework all this to prove.
So, can you explain the third step again?
This guy, this one.
No, the third one where n of t equal to n became x n plus 1 greater than t minus tau.
This guy. Okay. So, n t is equal to n. So, we are looking at some time t. We are conditioning on n t equal to n, right, and S n is equal to tau. The previous arrival occurred at tau, right. So, the previous arrival occurred at tau and n t is still equal to n, which means that there have been no further arrivals, right. So, this inter-arrival time cannot be smaller than t minus tau, right. So, what we are saying is that conditioning on n t equal to n is same as conditioning on x n plus 1 is greater than t minus tau, right. These two events can be shown to be the same. This would imply this and this would imply that, okay. Similar to, I mean, you can argue like this if you want, the recall box, right. I did it for the case n is equal to 1, we can argue similarly, okay. Yeah, so hence you are done proving that the time to the next arrival is exponentially distributed, and this exponential random variable is independent of the number of arrivals that have happened so far and the epochs of those arrivals. So, essentially it is independent of everything in the past, right. So, this Poisson process has this at every instant of time it statistically regenerates. It is as though a new process is starting every instant t, it is like a new process starts, right. It forgets everything that happened in the past, right. So, there will be no way to statistically tell the difference between. So, I start a Poisson process now, okay, and I keep running it. Somebody comes in at a particular time and starts watching the process. Statistically, there is no way to tell the difference. Okay. So, that finishes the memoryless property in this module. Next module, we will discuss increments of a Poisson process.